The Earth breathed with a steady rhythm, its surface alive with shifting, grinding, and building forces of geology. Deep beneath the crust, fiery molten magma swirled, while on the surface, wind and water shaped the landscape over millennia. Rocks, the Earth's storytellers, recorded every twist and turn of this epic tale. Among the many types of rocks that compose the Earth's crust, 3 distinct groups stand out, each born from a unique process. These rocks not only reveal the Earth's past, but also hold the keys to understanding the dynamic future. In this video, we will discuss the 3 rock types, look at how these rocks form, and how they are transformed by the rock cycle, as well as how rocks are grouped together, and core geologic principles that are used when observing rocks. Now, let's learn about our first rock classification, igneous rocks. The story begins deep within the Earth's crust, where molten magma churns, waiting for release. Igneous rocks, the earliest type to form, are created when molten magma or lava solidifies. Intrusive igneous rocks, such as granite, form when magma cools slowly beneath the surface, producing coarse textures. In contrast, extrusive igneous rocks like basalt result from lava cooling rapidly on the surface, yielding finer grains. These igneous rocks and their processes are shaped by tectonic activity, such as subduction zones and mid-ocean ridges. But the tale of igneous rocks doesn't end at its formation. Exposed to time and the elements, it faces the inevitable. Weathering is Earth's quiet sculptor. Rain, wind, and ice chip away at rocks over thousands of years. These forces lead to weathering, a key process in the rock cycle, which breaks down rocks at or near Earth's surface into smaller particles, which eventually contribute to sedimentary rocks. Weathering occurs in 2 forms, mechanical and chemical. Mechanical weathering involves the physical breakdown without altering their chemical composition. Some types of mechanical weathering include frost wedging, which is where water seeps into cracks, freezes, and expands, which causes fracture. Exfoliation, where pressure releases cause rock layers to peel. Abrasion, where wind or water transports particles that grind against rock surfaces. And finally, biological activity, where roots grow into cracks, splitting rocks apart. Chemical weathering, on the other hand, causes rocks to undergo mineralogical changes through reactions with water and atmospheric gases, especially in warm, humid climates. A few types of chemical weathering include hydrolysis, where water reacts with minerals to form clays. Oxidation, where oxygen reacts with minerals such as iron, causing rust. Dissolution, where water dissolves minerals like limestone or halite. And finally, carbonation, where carbonic acid from dissolved CO2 breaks down carbonate rocks. Both forms of weathering often interact, with mechanical weathering exposing more surface area, for chemical weathering accelerating the breakdown process. As these rocks are broken down, sediments are created. These fragments of pre-existing rocks journey through rivers, winds, and oceans, eventually settling in layers. Over time, these layers compact and cement into sedimentary rocks. Common types include sandstone, formed from compacted sand grains, and limestone, composed of calcium carbonate from marine organisms. These rocks are archives of Earth's history. Fossils preserved within their layers whisper of ancient seas, swamps, and forests, and each grain of sand or silt holds a clue to past climates and ecosystems. Sediments are classified into 3 categories. The first one being classic sediments, which are fragments of pre-existing rocks ranging in size from gravel to clay, transported by wind, water, or ice. Examples include sandstone and shale. The second being chemical sediments, which are minerals that precipitate from solutions such as halite from evaporating saline water or limestone from calcium carbonate-rich waters. And the final one being organic sediments, which are derived from biologic material like plant debris forming coal. Each sediment type reflects specific environmental conditions, making sedimentary rocks vital records of Earth's climatic and geologic history. But rocks are never static. Metamorphic rocks form when existing rocks are subjected to intense heat, pressure, or chemically active fluids, altering their texture and mineral composition without melting. This process, known as metamorphism, typically occurs deep within the crust or at convergent plate boundaries. For example, limestone turns into marble and shale transforms into slate. The intensity of metamorphism varies, producing low-grade rocks like phyllite or high-grade rocks like gneiss and schist. Each metamorphic rock is a testament to the intense forces that shape the Earth's crust. These 3 types of rocks, igneous, sedimentary, and metamorphic, are not isolated chapters in Earth's story. Instead, they are part of a vast, interconnected cycle. It begins with molten magma, which cools to form igneous rocks. These rocks can weather and erode into sediments, which eventually compact and cement into sedimentary rocks. Under heat and pressure, sedimentary rocks metamorphose into metamorphic rocks. If conditions intensify, metamorphic rocks may melt into magma, restarting the cycle. But it isn't always cyclical. Sedimentary rocks can weather into sediments, forming new sedimentary rocks, and igneous rocks can metamorphose as well. Metamorphic rocks can erode into sediments and sometimes metamorphose again. Plate tectonics drives these transitions, with processes like subduction creating magma, uplift exposing rocks to erosion, and mountain building triggering metamorphism. This cycle highlights Earth's dynamic systems where rocks undergo multiple transformations, recording geologic history over vast timescales. To keep track of this ever-changing Earth, geologists use a framework of stratigraphy to organize layers based on age, composition, and formation history. Lithostratigraphic units focus on observable physical properties, providing a framework for mapping and correlating rock bodies. These units are hierarchical, and we can begin with a formation, which is a primary unit defined by a distinctive lithological characteristic, such as the Morrison Formation, known for its Jurassic Age fossils. Another way to break it up would be a member, which is a subdivision of a formation representing a specific portion with unique features, like the brushy basin member of the Morrison Formation. A bed is the smallest unit, representing a single distinguishable layer, such as a volcanic ash deposit. A group is a collection of related formations, such as the Colorado Group of Cretaceous marine sediments. And finally, a supergroup is the largest unit, encompassing multiple groups or formations, like the Vindhyan supergroup in India. Type sections are reference points to find these units, enabling geologists to correlate them across regions. To identify rock formations and begin to stratigraphically organize rocks, there's a few principles geologists follow. The foundation of stratigraphy lies in three principles formulated by Danish geologist Nicolaus Steno. The first being the law of superposition, which states in undisturbed layers the oldest rocks are at the bottom and the youngest rocks are on the top. The second being the law of original horizontality, which states sediments are initially deposited horizontally. Tilted layers indicate later tectonic disturbances. And third, the law of lateral continuity, which states that sedimentary rock layers originally extended laterally in all directions, meaning that they were continuous across a wide area. And even if they were separated by erosion, like a canyon, similar rock layers on either side can be assumed to be a part of the same original layer. These principles enable geologists to reconstruct Earth's geologic history, interpreting sedimentary sequences and tectonic events. As geologists continue to reconstruct Earth's history, there are a few more core principles geologists live by. To further clarify relative ages, geologists refer to the intrusive relationship, which states intrusive igneous rocks are younger than the rocks they penetrate. They also use the principle of inclusions, which say that fragments within a rock, like a pebble in a sedimentary layer or xenoliths in igneous rocks, are older than the host rock. And finally, they use the principle of cross-cutting relationships, which states that faults or intrusions cutting through rocks are younger than the rocks they disrupt. Earth's movements profoundly influence the rock cycle. For instance, as mountains form, rocks are uplifted and exposed to weathering and erosion, producing sediments transported to depositional environments. Over time, these sediments form new sedimentary rocks, which may later metamorphose or melt, illustrating the interconnected nature of Earth's systems. This continuous transformation underpins the uniformitarian view of geology, emphasizing gradual processes shaping the planet over millions of years. Rocks serve as invaluable archives of these processes, documenting Earth's tectonic, climatic, and biological evolution. And there you have it, folks. I hope you enjoyed this video as we discussed how rocks form and the rock cycle. It would mean a ton if you guys liked, subscribed, and commented. It lets me know you are all enjoying these videos. And if you didn't know, you rock. Catch you later.